Hi, today we're going to be going over the Hamiltonian, which is quite an important quantity in classical mechanics. We're going to show that this expression for the Hamiltonian is actually equal to the negative of the partial derivative of the Lagrangian with respect to time, and that when the Lagrangian has no explicit time dependence on t, we get that the Hamiltonian is actually the sum of the kinetic and potential energies, and that it will be conserved, which is actually a special case of Noether's theorem. So to start off, we're going to be using a trick that we used to derive the Beltrami identity. If you haven't seen that before, you can check the description. But let's say we have a Lagrangian, and it is a Lagrangian over n coordinate spaces. So that could be written as t q1 q1 dot refers to the time derivative of q1, then you have q2 dot, so on and so forth, all the way up to qn dot. Right, so this is a typical Lagrangian for n coordinate axes. If you have, let's say, two coordinate axes, then q1 is x, q2 is y, and that's all you have. And usually we have, for the one-dimensional Lagrangian, you might be familiar with, just writing it like this. That is the case where n equals 1, really. So this is just a generalized form for it. What we're going to do is derive a Beltrami-esque identity for this. To derive a Beltrami-esque identity, we do the same thing we did for the Beltrami identity, and that is to take a full derivative of the Lagrangian with respect to t. And using the chain rule, that would be partial L over partial t times partial t over partial t. Well, this is just 1, so we could just not write it. And then you would have partial L over partial q1 times partial q1 over partial t. Now, this is actually just q1 dot, because, well, it's the time derivative of q1. So we can compactly write this as q1 dot. Then you'd have to do the same for q1 dot as again. So that would be partial L over partial q1 dot times partial q1 dot time over partial t. And you can realize that this is actually q1 double dot, or the second derivative of q1 with respect to time. So that would be partial q1 dot dot. And you do the same thing for each, you could say, parameter, and you can actually write this quite compactly in summation notation. That would turn out to be the sum from I equals 1 to n of partial L over partial the ith coordinate axis times qi dot plus partial L over partial qi dot times qi double dot. And you can see that that is actually exactly what we had, just in a summation notation, so that it goes for all the parameters. Right, so what we're now going to do is actually use the Euler-Lagrange equations for this Lagrangian. We know that for this Lagrangian, the Euler-Lagrange equation would be partial L over partial qi equals to the time derivative of partial L over partial qi dot for each coordinate axis. So that would be for I equals 1, 2, 3, dot, 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 all the way up to n. This is quite a general theorem, and it's also very simple to see. So what we're now going to notice is that this looks quite a lot like the expression we have in our summation. If you notice this, all that's missing really is just this, and we could just perhaps artificially add it in by just multiplying both sides of the Euler-Lagrange equations by qi dot. Nothing wrong with that, really. And now we have an expression for what we have here. It's something that may look a little bit more complicated, but just wait for the magic to happen. You'd have the full derivative of the Lagrangian with respect to time equals the partial derivative of the Lagrangian with respect to time plus sum from I equals 1 to n of now this is well, it's going to be d over dt times the partial derivative of the Lagrangian with respect to qi dot times qi dot plus partial L over partial qi dot times qi double dot. Now, do you notice something here? Let's take a closer look at what we actually have here. Well, some of you might instantly recognize this as an application of the product rule. Well, how is that? Well, this is simply just the derivative of partial L over partial qi dot times qi dot. And well, if you do actually apply the product rule on this for differentiation, you get the same thing. So we actually have a quite an interesting expression now. We have that partial L over partial t equals, sorry, that's not partial L, that's the full derivative of the Lagrangian. Full derivative is very different from the partial derivative. Equals to the partial derivative of L over with respect to t plus the sum from I equals 1 to n of the derivative of partial L partial qi dot times qi dot. What we're going to do now is move this to the other side, and we know that differentiation is commutative, so we actually would get a pretty nice identity here. That would be that the derivative of the Lagrangian minus a sum from I equals 1 to n of partial L over partial q dot I times q I dot equals to the partial derivative of the Lagrangian with respect to time. Right, so this is actually a form of, this is actually, you could say, a generalized Beltrami identity, and we're going to see how very soon. We know that the Hamiltonian is actually defined as the sum from I equals 1 to n of the partial of L over the partial of qi dot times qi dot minus L. And well, this is because this expression right here is actually just the momentum in the ith coordinate axis. So therefore, and that's how the Lagrangian is, that's how the Hamiltonian, I mean, is derived. So we actually get that, well, if I just take a negative sign out of here and multiply both sides by -1, I'd actually get that the derivative of the Hamiltonian with respect to t is actually negative of the partial of the Lagrangian with respect to time. Now, let's say our Lagrangian is time independent, and what that means is that there is no explicit dependence on t in the Lagrangian. For a partial derivative, that means that all other parameters are treated like a constant, and so partial L over partial t would actually be equal to 0 when there is no explicit time dependence. What does that mean? That means that the Hamiltonian is actually going to be constant because, well, its derivative with respect to time is 0. So as time goes on, as the system evolves, whatever you want to say, the Hamiltonian gets conserved only when the Lagrangian is time independent. But what is this conserved quantity? Let's look a bit deeper into this. So we know that the Hamiltonian is defined as, well, that's the sum from I equals 1 to n of partial L over partial qi dot times qi dot minus the Lagrangian. Well, we know that this is the momentum, and this is easily seen by differentiation. We know that the Lagrangian is the kinetic energy minus the potential, and if I take the derivative with respect to q dot and that too of the ith axis, this vanishes. For this, we can split up the kinetic energies into something like this. For each coordinate axis, there's the associated kinetic energy and blah blah blah, and all of the ones other than half m qi dot squared cancel out, and when you differentiate this, with respect to qi dot, you'd get mq dot, which is actually the momentum. So this is mqi dot, which is actually, well, qi dot you could say is the velocity in the ith direction, but you also get qi dot multiplied again, so that would actually be m velocity in the ith direction, so v squared. Right, so the Hamiltonian, now we could write the Hamiltonian is equal to the sum from I equals 1 to n of this minus the Lagrangian. Well, the Lagrangian is simply equal to the kinetic energy minus the potential, so if I plug this in here, that means the Hamiltonian would be, well, I can split up the kinetic energy again, and we'd get this expression then. You'd get mvi squared minus half mvi squared, and then outside the summation you'd get plus potential energy. Well, this is simply half mvi squared as well, and this is the sum over all coordinate axes, so that's actually the total kinetic energy. But hey, we get that then the Hamiltonian is the total kinetic energy plus the potential energy, which is actually the total energy of the system. And we know then that when the Lagrangian is time independent, this total energy is actually 0. So the total energy is a conserved quantity when the Lagrangian is time independent, and that is actually a special case of Noether's theorem. So we've proven that if we have this, that we get this equality, this cool identity, which is actually a generalization of the Beltrami identity, which then would imply that the Hamiltonian is conserved when the Lagrangian is time independent. And as you'll see very soon, that's a special case of Noether's theorem. One thing to mention is that the normal Beltrami identity that's commonly known is usually applied for functionals of this form. Or you could, rather in a physics term, you could say that's the Lagrangian of t, x, and x dot, and the same wouldn't be possible on a generalized functional for n coordinate axes. That's why we had to derive a generalization of the Beltrami identity on our own. This is actually a mistake I made myself in the last post, but I rectified it. Anyways, I hope you guys enjoyed this derivation. Please leave a like and subscribe.